Welcome to the paper Shortcomings of Top-Down Randomization-Based Sanity Checks for Evaluations of Deep Neural Network Explanations. We analyze properties of top-down randomization proposed in the paper Sanity Checks for Saliency Maps in NeurIPS 2018. Our motivation is a discrepancy between model faithfulness AUPC measures and sanity check SM measures in the ranking of attribution methods. We find that sanity check SM minimization is sensitive to noise. Adding noise results in a better SM minimization. Furthermore, we find that the following assumption does not hold. Randomizing several top layers results in complete randomization of explanation. The model is partly unchanged for irrelevant features, for features propagated along residual connection shortcuts, and for highly activated features in the highest unrandomized layer. Okay, let's go into the main paper and look at the discrepancy observed between sanity check evaluation and faithfulness evaluation. So here we measured the SM scores for the sanity check evaluation, and we measured them for three neural networks: RSN50, ADENSAT 1-to-1, and an EfficientNet B0. And all these networks are pre-trained on ImageNet, and lower is better. What we can see is that gradient-based methods perform best under this test. These are in these bluish colors. Yeah, this is the principle: gradient times input, and integrated gradient. We can observe here guided backprop, which performs really not well under this test, and we can see LRP, which performs somewhere in the middle, but also not really good. If we look at model faithfulness, like occlusion testing, that means that we take in principle the regions with the highest scores, we blur them, and we measure the decrease of the softmax score. Then we see the opposite picture. Gradient-based methods perform really not so good, guided backprop performs really better, and LRP performs a little bit better. And now we can ask ourselves, of course, what's the reason of this behavior? Well, we can look at the structure of the SM measure. And we should note that in usual image quality assessments, unlike here, the SM measure would be maximized. Here it's minimized. And the SM measure has a covariance term, patchwise covariances. And of course, we can make the absolute value of this term small if we use attribution maps which have 0 or close to 0 covariance. And this is formalized in Theorem 1. And what are the consequences of this? Well, first of all, we can achieve very low SM scores in the sense of good performance under sanity checks when we add noise to attribution maps. Secondly, if we would use SM minimization in order to select hyperparameters of attribution maps, it might select us those hyperparameters with very noisy attribution maps, which is undesirable. In total, one cannot disentangle the effects of model randomization from the amount of noise in an attribution map process in this type of sanity checks. But there is more to it. Actually, randomization leaves the model and the explanations partly unchanged, and it does so in three categories. The first thing is something very simple: preservation of irrelevance of explanations. That is, we have a neural network with a bottom unrandomized part and a top randomized part. And if there is an input feature which is in principle ignored by the bottom unrandomized part, then this irrelevance is also preserved under any randomization of the top part. And this is, for example, shown in figure 4. We have an example image. This is the original attribution map computed using LRP. And it has here a lake. And now we randomize the attribution maps. And for the lower part of the lake, no matter what we do, it never gets any relevant scores. And it might make sense because this lake is just completely ignored by the neural network. There is further more to that. There is a preservation of a baseline explanation in networks with skip connections. So what's the point of this? Well, we have a neural network with a skip connection here, and here we have the skipped convolutions. And if we would randomize these convolutions, then in principle the impact on the total network is limited, because here are n randomized features added from the bottom. And we can see this limit of change in the output logits, where we see that before and after randomization there is a quite strong linear combination to be observed. And we can also see this in figure 7, an example, where we have example images, original attribution maps, randomized attribution maps, where we propagate the scores to all paths, and randomized attribution maps where we propagate only through the weighted path. Yeah? When we propagate only through the weighted path, there's lots of change. If we take the sum of both parts, then the randomness is quite limited. But there is one further effect, which is general and holds for any neural network, and this is the following effect. Highly activated features in the last unrandomized layer have a strong contribution to the activation in the next weight randomized layer, in the sense that it holds with high probability over draws of weights from a zero mean random normal. This is formalized in theorem 2, where we just state if we have a set of large activations, a set of small activations, then after multiplication with random weights, and the probability that this small set of activations overtakes the large set of activations is something like the tail CDF of a Cauchy distribution. And one can see this again in figure 4, where we have the original attribution maps and the attribution maps for randomized networks, and we see that certain dominant structures, they are approximately preserved in an absolute value. What are our consequences? First, the scores of sanity check measures should be used only as a binary test to support the presence or absence of an effect of randomization on the explanation. We advise against the use of sanity check measures to rank attribution methods based on the partial robustness of models against randomization identified in this paper. So lower SM is not automatically better. And we suggest to consider a use case dependent mixture of different measures for explainability quality. There is no the one explainability evaluation measure to rule them all. Thank you.